Hey guys, and we're going to just talk about some probability basics, right? So basically, what is this? Probability is an action, right? It's rolling a die, or it could be tossing a coin, or selecting someone out of a crowd. Right, so there's lots of actions, but the idea is that every action is going to have a single outcome. So when you roll a die, a number will come up. When you select a card out of a deck of cards, a card would be selected, just one. And it is uncertain, so a lot of times you'll hear the word fair die or unmarked, or sometimes you'll even just see random, so a random person. All right, an event is any collection of results or outcomes of a procedure, such as rolling an even number. A simple event is an event that can't be broken down, right? So an even number can be broken down. We know on a six-sided die that would be 2, 4, 6, right? So a simple event is just rolling a 2. Right, that would be a simple event. Sample space is all possible simple events. So when we're thinking of a sample space of rolling the die, we could get 1, 2, 3, 4, 5, or 6. All right, for example, if we use B to denote a boy and G to denote a girl, a single birth would be an event would be just having one girl, a single birth. Our sample space, though, could be a girl or a boy. If it's 3 births, and we're saying order matters, so we could have 2 boys and 1 girl, that's one event, but actually there are 3 simple events that constitute 2 boys and 1 girl. Excuse me. So that's all the events that could happen with 3 births. All right, some notation just so we're all on the same page. Most of the time when you see a capital P, that's going to denote probability. Any other letter usually denotes just a specific event, which you're told of at a prior event. So if you see this, P and in parentheses A, this is just stating the probability of event A occurring. How we find probability is we're going to use the F over N rule, where F is the number of ways that event can happen and N is the total number of possible outcomes. Don't worry, we're going to do lots of examples. Now the idea of that is that's our theoretical probability, right? That's just theoretically, that's what's going to happen. Think of when you toss a coin, the probability of getting heads. So getting heads, that's 1 is a head out of 2 sides, so theoretically you get half a chance. Now, where we get that and how we can prove that is using the law of large numbers. Law of large numbers states that if we roll the die over and over and over and over and over again, ultimately we would get around 50%. And I did that with one class one time, just gave them a lot of pennies and they just started tossing the coins. And you could see that we started with 200 tosses and only 52%, or 0.52 of them, were heads. But the more we rolled, the closer it got to that probability, that theoretical of 0.5. You can do that also with computers now, right? We can simulate that. So not any single computer is going to give you the exact same value, so you can see this one was under 50% for a while, but then as you got higher and higher, it got closer to 100, or got closer to 50%. All right, so let's do an example. Rolling a die. So we just said our sample space was 1 through 6. All right, rolling more than 4. So more than 4, it constitutes just 5 and 6, so it doesn't say at least 4, right? So more than 4 means more than 4. So that would be, and I'll just put that, that's 2 over 6, which is 1/3, or 0.3333 to 4 decimals. Rolling at most a 3, the most it can be is a 3, so that includes 3, right? So that probability is 3 out of 6, because there's 3 values out of 6, which is 1/2, or just 0.5. Half of the numbers are at most a 3. All right, let's look at 2 dice. So 2 dice, we have 36 outcomes, right? So notice that having a 4 and a 1 is slightly different than having a 1 and the 4. We have those two different ideas, kind of like when we were talking about the 2 boys and 1 girl. All right, so if we roll a sum of 7, there's 7, 7, 7, 7, 7, 7. So there's 1, 2, 3, 4, 5, 6 values out of 36. So 6 out of 36, which is 1/6, and that equals 0.1667. All right, at least a sum of 9. So at least a 9 would be 9, 10, 11, 12. That's at least the 9. The least amount can be a 9. So let's see. 9's right here. And there's 10, there's 11, and there's 12. So we're looking at this bottom section. And there's 4, 7, 8, 9, 10 of those. So that is 10 out of 36. And 10 divided by 36 is 0.2778. All right, let's draw a card. So our sample space, there are 52 cards, right? They range from ace, diamonds, spades, and clubs. Ace and diamonds are usually red, and spades and clubs are usually black in a standard deck. And they go from ace, and then 2 through 10, then jack, queen, king. The jack, queen, king are considered face cards. Ace is not a face card because it lacks something very important, a face. All right, so now we have our sample space. If we wanted to draw a diamond, we could see that there are going to be 13 diamonds. So 13 out of 52, which is 1/4. Probability is a 0.25. Drawing a face card. So there are 3 face cards for each suit. And the suit is the heart, diamond, spade, and club. So 3, 6, 9, 12. 12 out of 52. And 12 divided by 52 is 0.2308. Drawing 11. Whoops, wrong way. There's not an 11, right? There's not 11 at all. So that would be 0 out of 52, which is just 0. So you can have a probability of 0. When 3 children are born, the sample space we said was this lovely thing. So notice there's 1, 2, 3, 4, 5, 6, 7, 8, 8 ways. Assuming that boys and girls are equally likely, find the probability of getting 3 children of all the same gender. So all boys, or it could be all girls. So that would be 2 out of 8, which we said was 1/4. Oh, and I think I actually have that. Yep, 0.25. Okay, so some key facts. Probability in an event is always between 0 and 1. So you can't have negative probability, and you can't have a probability over 1. If you're thinking of percent, then it's 0% is the lowest, 100% is the highest. We can have 0%, just like we saw, and we can have 100%. If you get a 0%, that's an impossible event. If you get a 100%, then that is a certain event. So if we think about it, we have 0 is impossible all the way to 1 is certain. So right in the middle is 50%. And so we kind of have this likely events and unlikely events. And we think unlikely is somewhere over here and likely is up here. Another way to think of it, if you just toss a coin, you're going to get an even chance, right? 50% chance heads, tails. Certain is going to absolutely happen. And then it gets lower and lower to impossible. However, we have a cutoff for unlikely events, and we call it 0.05 or less. So getting a probability of 0.04, we consider unlikely, as well as 0.05, so 5% or less. All right, let's do just a little bit more. This time we have a frequency table, and we can see it's the age distribution of murder victims between 20 and 59 years old, and there it is, and there's the frequency. So we're going to find someone at random. All right, so that means we're going to have uncertain outcome, and we're looking between 40 and 44 years old inclusive. So there's 40 to 44. So that's 1,152. But now I need the total number. And how do I get the total number? I'm just going to add all of those up. So let's see. I think I remember it, but I'm just going to check my work really quick. You might hear me punching on my calculator. All right, yep. So if, whoops, oh no. So if I add that up, that's 10,810. So that's what I'm going to divide by. So I have 1,152 divided by 10,810, and that is 0.1066. Notice that it is a small probability, but we wouldn't consider that unlikely. Let's look at least 25 years old. At least 25 means the minimum is going to be is 25. So 25 on up. So we could add up all these and we would get 8,000. Or another way we could do it is we know the total is 10,810. We just don't want that one. So we could subtract and we'd still get 8,000. So two ways we could do that. Pretty easy, hopefully. And we get 0.7401. So notice that this is on the likely scale. And if we look under 30 or over 54, under 30 are these two. Or over 54, that's this. So we're going to add what I just circled all together. Because we don't care which one it is, we just want one of those, and we get, where's my pen? 5,247. And again, we're going to divide by the 10,810. And I get 0.4854. All right, let's do, one more example. Suppose that 5 out of the 30 students in statistics will work on their assignments every day. On each day of the year, one of the students are given an A if they were working online that day. Don't we all wish? On approximately how many of those days would one of the 5 students be chosen? So we're assuming on each day of the entire year, of the year. All right, so I know my probability, there's 5 out of 30, and that probability of a student always working on their homework is 0.1667. All right, but this is saying how many of those days would one of these students particularly be chosen at random. Okay, so we know that there's 365 days in a year. So basically, we're just going to say 365 times our probability. And that would tell us how many days we would get one of those particular 5 students if we were just choosing 5 students out of the 30. So 61 out of 365 days, they would choose one of those. All right, this is just an overview of the basic probability rules.